Okie doke, we are seriously on the downhill slide now, almost to the end of the semester. The light at the end of the tunnel, it is not an oncoming train, trust me. So this is where we're at. Basically, we have stuff coming up in chapter 22 and chapter 23 that's really pretty much the same old, same old. You're going to see that these chapters are a review of electrophilic addition and a review of elimination. So 22 and 23 could really be crammed into one chapter, so don't freak out about the pace here. Then we'll cherry pick in chapter 26. That's just a fun way to review a whole lot of chemistry from the year long in the context of polymer chemistry, which is a huge area of chemistry. So that said, let's move on to this big overview of electrophilic aromatic substitution. That's what the next two chapters really are all about, EAS. So we are well familiar with nucleophiles that are pi electrons. That's one of the first set of nucleophiles we learned. Remember way back when we were looking at some alkenes and we determined that they could add extremely strong acids. Acids like sulfuric acid or HCl that have negative pKa's. Well, now we're finally going to look at those pi electrons that we have completely ignored for 14 weeks. The pi electrons in an aromatic ring. They are even weaker nucleophiles than alkenes and alkynes. They do not want to react. And why don't they want to react? Well, as before, we're making a high energy carbocation intermediate. It doesn't want to go, and the reaction doesn't want to go uphill. And the other reason why is because if that pair of pi electrons reaches up and reacts with an electrophile, you destroy the aromaticity of the aromatic ring. So it's got nothing going for it. This is evidenced very clearly if I take cyclohexene, like the cyclohexene you guys made way back in OChem 1 lab. Remember when you added that dark red bromine? The reaction that immediately occurred, which you could tell because the orange color from the bromine instantly dissipated. So, reaction with an alkene, super fast. And you get the addition of bromine across the double bond via the bromonium ion to give you the trans dibromo compound. I can add bromine to benzene and stir until the cows come home, and nothing will happen. The orange color will just stay there and stay there and stay there. So if I am actually going to get this kind of reaction to take place, I am going to have to use a super strong electrophile to make this thing happen. And as you will see, basically we do that by supercharging the electrophiles by reacting them with something else first to activate them. So just as we saw in chapters 20 and 21, that mechanism we saw over and over and over again, up, down, out, up, down, out. You're going to see the same thing now. It really doesn't matter what the electrophile is or the specific nature of the aromatic nucleophile. You're going to see the same electrophilic aromatic substitution mechanism. So the first part is, as we've already alluded to, you've got to make that electrophile a lot more electrophilic. So, for example, chlorine by itself, bromine by itself, they're not going to add to your aromatic ring. But if I take a Lewis acid, which little Gen Chem review is an electron pair acceptor, well, we happen to have an electron pair here. So, oops, not there. Wait a minute. What's electrophilic about aluminum trichloride? Well, get out your periodic table, look and see where aluminum is. It's right underneath boron. It means it's group 3, which means just like boron, we'll just put a box here for our element. It's going to be trivalent and therefore possessing an empty p orbital. It only has 6 electrons. It would definitely like to have 8. So that electron pair is going to go straight for the aluminum to give me this guy, which looks pretty weird. A negative charge on my aluminum, a positive charge on my chlorine. Well, that's not going to last. So it falls apart to give us, woohoo, one serious electrophile, positively charged chlorine, and the counterion, that being this chloroaluminate. Don't worry about the names, I'm making them up. In any case, the whole point is the Lewis acid activates the chlorine to make it a lot more electrophilic. Same thing can happen with an acid chloride. We know acid chlorides are pretty electrophilic, but watch this. We can make them really electrophilic. So where's my electron pair? Right there. Reacts with the aluminum to give me this guy. And this is all wrong, so I should stop and say, wait a minute, that's reasonable, but it's not going to get me where I want to go. So instead of the lone pair on my carbonyl reacting with the aluminum, we'll see the same thing happening as we saw up above. So when my chlorine reacts with the Lewis acid, and there's bunches and bunches of Lewis acids that can work in this role, well, then I've got the same kind of complex as I had above, negative and positive here. What can happen next? Now we invoke that lone pair on oxygen, kick that down, kick that out, and what do you get? Oofta. A major electrophile right there. We could even draw a resonance contributor. Holy cow, is that electrophilic. This is called the acylium ion. So we have to make these unbelievably electrophilic reagents in order to get our very unreactive aromatic ring to react with it. So that's the second step. You make this supercharged electrophile, and then it adds to the aromatic ring. And this should look just like an electrophilic addition reaction. So out pops the pi electrons. That means I'm going to put a positive charge on the other carbon, and so you should be thinking about regiochemistry just like we did way back when. So if this were just electrophilic addition, whatever nucleophile I have present would just then go ahead and attack, and there you go. I'd add across a double bond. But no. What happens instead is that an elimination reaction takes place because, and this should look and is the exact same elementary step as you see in E1. When that happens, we go from our highly unstable carbocation to our extremely stable aromatic ring. So by an elimination step and deprotonation of that hydrogen, let's try that again. There we go. deprotonation of that hydrogen gives us our aromatic ring, and that is the serious driving force for this electrophilic aromatic substitution reaction. You see, I have substituted that hydrogen with a chlorine. So we say that this is a highly unstable carbocation, and it is, but we have evidence that this reaction takes place, and the reason we can make this carbocation is because, yes, it is stabilized somewhat due to resonance delocalization as this positive charge is delocalized around the ring. And again, I will just give you some foreshadowing. This will have some very important implications in terms of regiochemistry, what we'll get to in the next mini lecture. Bottom line is, it's the resonance hybrid, as usual, that we want to pay attention to. So we take all three of these resonance contributors and put them together to notice that in our aromatic ring we build up a positive charge of those three carbons. Keep that in mind. Alright, so here's the rest of chapter 22 and chapter 23. Basically, we've seen a lot of these electrophiles before. Certainly we know the proton. We've seen carbocations. We've seen halide electrophiles in the form of things like chlorine, bromine, and N-bromosuccinimide. Now we see how we can activate them. We're going to learn new. This guy, the nitroso cation, this sulfate sulfonium cation, and we've already indicated how we're going to form our acylium ions. Basically, pick an electrophile, any really strongly activated electrophile, and react it with an aromatic ring, and you get substitution. So we can put, for example, a methyl group on an aromatic ring now. We can put a halide on an aromatic ring. We can make nitro aromatic rings, nitrobenzene, trinitrotoluene, aka TNT. We can make surfactants and detergents by sulfonating our aromatics. We can make tosic acid. And now, very excitedly and enthusiastically, we can go from an aromatic ring to, for example, a ketone. Something that you couldn't really do very easily, not in one step before. Try as you might. Alright, so some other introductory overview types of information. This chapter is well placed at the end of the semester because it's going to give you lots of good reinforcement of electron movement mechanism and resonance contributors. And it's very handy because it will, allow us to open up a whole nother avenue of synthetic possibilities. Interestingly enough, what I'm telling you is that it's a piece of cake. Well, it's not a piece of cake, but we can certainly put electrophiles on aromatic rings because we're talking about electrophilic aromatic substitution. But it should certainly cause you pause when you try to think about maybe making aniline or phenol, because Lord knows we're not going to have any electrophilic OH groups around or any electrophilic amino groups floating around. So that is a question as yet to be answered by us. The other nice bit about this chemistry is that, well, we already know how to manipulate some of these aromatic substituents. For example, we've learned how to oxidize, or maybe we haven't learned this yet. I don't think we have learned this. I can't remember if we've learned this, but we're going to review it if we haven't learned it. The bit about how do you convert a methyl group into a carboxyl group. We're also going to see how we can get from a nitro group, clearly oxidized, put hydrogens on instead of the oxygens, that's definitely a reduction. And we'll see, how do we get an OH group on the aromatic ring? Oh, you might find out that Carpenter perhaps hasn't been quite as straightforward with you as you would like to believe. So that's the big overview. We must end by nomenclature, of course, which is terribly important, and I just can't seem to convince you of that. But what is the name of this aromatic compound? Well, it should be quite obvious that this is a Ferris wheel. Get it? Yeah, okay. That's all right. See you in class.